Hi, this is Jeff with a friendly introduction to hash tables. Before we dive into what exactly hash tables are, let's first look at why we would want to invent such a thing. What exactly is the motivation for inventing a hash table? Turns out we have a lot of things that are structured like this, some names and some details related to these names. For example, all Wikipedia article titles and their contents, or a list of names corresponding to personal information. In hash table jargon, this is called a key-value pair. Here's the motivation. Given a name among many names, we would like a fast way to look up the corresponding content. Or given a key among many keys, look up the corresponding value. A naive way to deal with this lookup problem would be to store all key-value pairs in a huge list, read out each key, and check until we have a match. This can be really slow when you have a lot of elements. In fact, on average, the lookup time will be proportional to the number of elements. Of course, we can do it faster than that. You might have noticed the problem with this. Reading out a value given a position in a list is fast, but matching each key is slow. This is the key idea. If we had a systematic way of translating keys to positions, we would reduce the lookup problem to the fast problem of reading a position from a list. The translator that maps a key to a position is called the hash function. Here's an example. Let's say we have key-value pairs that denote fruit prices, like apple for $1, banana for $2, and apricot for $3. A simple and really bad hash function, for example, could take the key and output the position of the key's first letter in the alphabet. A would be 0, B would be 1. A hash table is two parts, a hash and a table. It can do three things: add, lookup, or delete a key-value pair. Overall, they are the same. Give them the key, find the position, and do something with the key-value pair at that position. Let's add the three elements to the hash table. Apple, position 0, no problem. Banana, position 1, no problem. Apricot, position 0, problem. We already have something there. What do we do? This is called a hash collision. Our simple hash function sent different keys to the same position. In fact, even if we had a sophisticated hash function, hash collisions can still occur because there are infinitely many things we might want to store, but limited positions we can store them in. We can easily patch this up by storing both apple and apricot at the same position, kind of making the entire table a list of lists. And when we need to look up a key, we hash to find its corresponding position and go through the list at that position until we find a match. Of course, this reverts to the dump method we discussed earlier for looking up. If we store too many elements in one position, it becomes slow again. That's why hash collisions are problematic. We want to limit their occurrences. To do that, we can have a longer list with more spots to store the key-value pairs and better hash functions that send different keys to different positions. You've probably used hash tables before as a built-in feature. In many languages, Python for example, dictionaries are implemented using hash tables in the background. When you write a dictionary, you are using a hash table someone programmed for you. This video didn't cover the implementation details of hash tables, but I hope that it provided a conceptual understanding to do further exercises. Thanks for watching.